Back in 1994, Dubai was largely flat desert and coastline, bearing very little resemblance to the towering, futuristic metropolis you see today. Back then, Sheikh Mohammed bin Rashid Al Maktoum had an incredibly ambitious mandate. He wanted to construct a landmark so iconic, its silhouette alone would put Dubai on the global map. Architect Tom Wright translated that ambition into a simple sketch, the curved shape of a traditional Arabian dhow sail. But the mandate came with a bold demand. This structure had to be placed 280 meters offshore, right in the middle of the waves. This diagram highlights a project-killing geographical discovery. Normally, a skyscraper is anchored securely to shallow bedrock, but when engineers surveyed the seabed here, they found that the solid rock lay nearly 180 meters below the ocean floor, far too deep to reach. They were suddenly faced with an engineering nightmare. They had to figure out how to support a $1 billion, 70,000-ton megastructure entirely on shifting ocean sand. Moving the project back to the safety of land would have solved the problem instantly, but compromising on the location would defeat the entire purpose. To serve as the ultimate symbol for Dubai's future, the structure had to conquer the open water. Work had to begin directly in the ocean. The construction site was completely isolated, surrounded by salt water with no solid ground for heavy machinery. The crews started by driving massive reinforced concrete piles into the seabed. They hammered 230 of these columns, each 40 meters long, deep beneath the ocean floor. This diagram illustrates the only force preventing sinking, skin friction. The foundation relies entirely on compacted sand gripping the pile. Outward arrows represent this frictional force holding it in place. If this friction failed load testing, the entire 70,000-ton concrete structure would collapse. To transition from subsea foundation to surface construction, engineers needed a dry workspace. They drove corrugated steel into the seabed to form a temporary boundary, successfully pushing back the ocean. Inside that boundary, they pumped in a mixture of seawater and loose sand. Powerful machines vibrated the mixture relentlessly until the water filtered out and the sand solidified into actual land. But an artificial island made of sand is highly vulnerable. The Persian Gulf experiences severe storms, with waves powerful enough to wash standard reclamations entirely away. Instead of trying to build a solid wall to block the waves, engineers deployed concrete honeycomb armor blocks. When violent water hits this geometric shape, the wave energy enters the hollow spaces and immediately dissipates into harmless foam. The team successfully created a 7.5-meter-high artificial island that could withstand the sea. But as they prepared to build upwards, they faced dangerous new chemical and structural hurdles. The foundation presented a massive logistical puzzle. The 70,000-ton concrete base had to be poured continuously in a single, non-stop operation. If the pour stopped midway, a weak joint would form, permanently compromising the building's structural integrity. This created a severe thermodynamic crisis. As concrete cures, it generates enormous internal heat. If temperatures inside the massive block exceeded 70 degrees Celsius, the foundation would crack from within. Looking at this diagram of the curing process, we can see their solution, a sprawling internal network of pipes. Cold blue lines of chilled water circulated continuously for weeks to neutralize the spreading red heat pockets, keeping the core temperature stable. With the base secure, the tower began to rise. Rather than building traditional scaffolding up from the artificial island, they utilized a jump form system, specialized rigs that lifted themselves upward, pouring concrete floor by floor. But as the structure reached 300 meters into the sky, it encountered extreme environmental threats. At that altitude, violent coastal winds exert massive lateral forces against the building. The 9,000-ton steel framework wrapped around the exterior functions as a vital aerodynamic shield, bracing the inner tower against immense wind pressures. Enclosing the structure required absolute precision. The iconic white sail is made of custom-cut fiberglass panels coated in Teflon. Each piece had to be tensioned flawlessly to ensure the wind couldn't flutter and tear the membrane apart. The engineers then pushed the limits of gravity with two exterior attachments. They suspended a restaurant extending 27 meters out into open air, and 210 meters up, they cantilevered a helipad directly over the crashing waves. Conquering these escalating vertical forces, from engineering deep-sea friction to deflecting high-altitude winds, proved that entirely new methods of offshore construction were possible. The brutal, salt and wind-battered exterior construction stood in sharp contrast to what visitors found inside. Passing through the doors revealed a perfectly insulated, soaring 180-meter-tall interior atrium. The sheer scale of the $1 billion luxury budget was immediately apparent. Walls were wrapped in precious Italian and Brazilian marble, and workers spent countless hours hand-applying nearly 1,790 square meters of genuine 24-karat gold leaf. The aquatic engineering extended inside as well, with massive aquarium glass panels specifically built to contain and withstand the intense pressure of nearly 1 million liters of water. It took a workforce of 2,000 people dedicating 5 years of their lives to complete the massive undertaking, finally opening the doors to the world in December 1999. The completion of the Burj Al Arab demonstrated that Dubai could successfully manage the capital and engineering talent required for projects of this scale, setting a new standard for the city's future developments. By mastering the science of building upon unstable ocean sand, Dubai proved its ambition to the globe. They created the foundational symbol that allowed an entire city to rise around it.